Hello again, it's Mr. Tuxford. We're continuing our Level 3 Physics Investigation step-by-step guide. Right now, we are up to the error bars. Right, so we have plotted the linearized graph. As you can see that over here, that's where we ended off last time. Alright, but let's delete that, because we are now going to add the error bars. So error bars are a way of representing the uncertainty in our measurements on our graphs, and then from there we can then work out the uncertainty in our gradient and y-intercept, and then can write a conclusion stating if our measurements are within the experimental range. So uncertainties. Last time we worked out the absolute uncertainties. So for square root of length, we had these values over here. Let me just highlight them yellow. Oh, that's so bright. Where's the less bright yellow? Alright, let's go purple. So our uncertainty in square root length, as well as our uncertainty in the time period. So remember that for the time period uncertainty, we first used the half range rule, and we found that the uncertainty by reaction time divided by 10 was greater than all of the uncertainties from the half range rule. So we will use the greater of the two. In this case, it's 0.03 seconds for our time period uncertainty. So let's add the error bars. So to do that, with your graph selected, you hit the chart elements button, or if you're on Mac, chart design, add chart element, right, same thing. Error bars, you hit the tick box, and you'll notice we have these large error bars. Now those are just the default error bars, which is completely useless. So from here, we need to specify the values for the vertical error bars, so that's the time period, and the horizontal error bars, that's the square root length. So let's start with the vertical error bars. If you carefully click, see, that wasn't careful, carefully click, there we go, got it, the vertical error bars, you'll see it's now selected the vertical error bars. On the right panel, right, you can style them, but more importantly, we go to the error bar options tab. We do want both the positive and negative direction, right, plus and minus. Cap or no cap, wonderful. So cap is just the bar at the top. Leave the cap on. And then finally, the error bar amount could either be a fixed value, a percentage, or for us, we will use the custom option. And so we hit custom, and now we need to specify the values. So if I just scroll across here we go, specify the values. And for your positive error value and your negative error value, it would be the absolute uncertainty for that variable. So vertical is period, so it'll go up by 0.03 or down by 0.03. You'll notice when I did that, it left this bit at the front. You do not want that, you'll get an error. And just, yeah. So double check. Positive error value, we selected it, we click and dragged 5 error bar values. Negative, the same 5 as well. And when you hit OK, have a look at the graph. What happens to the vertical error bars? It looks like they disappeared, but in fact, since our uncertainty is quite low, because we did 10 measurements and divided by 10, if you zoom in far enough, you'll get to see them. Oh my goodness. And if the dots are kind of in the way, which in my case they are, if you click the dot, you go to the fill and line, the marker, you could make this no fill and no line. Now we've kind of removed the data points, but that's just to see that the error bars are still there. So you could have the solid fill, marker options. What do we want? Oh. Transparency. Oh yeah, here we go. If we up the transparency, that's a little bit easier to see. Again, completely optional, but just to verify that you do have vertical error bars. So let me zoom out again. So that is the vertical error bars, and we specified the value to be 0.03. If your half range rule had a greater value, make sure that uncertainty 1 period. In this column, just pick whichever is the maximum between your half range rule and your reaction time. And then it's this column that you'd select for your uncertainty. But in our case, the reaction time one was the maximum for all values. Okay, now the horizontal error bars, just like for the vertical ones, you select, so click the edge of the horizontal error bar. And if the window doesn't pop up on the right, try like click it again, double click, there we go. Like before, we would like custom error bar amount, specify the value, and here we grab the absolute value in square root of length. That's all of these ones right here. So click and drag, and again, click and drag. You'll notice that just get rid of that curly bracket 1 plus. So in the positive and negative direction, we have the same amount. Okay. And again, our error bars are very tiny. And that is because when we square rooted length, we halved the uncertainty as a percentage. So we have added both vertical and horizontal error bars. If in your experiment the error bars are larger, that's totally fine and is actually expected, because you are expected to have uncertainty in your experiment. Cool. And you could copy this into your report now, but there's still a few things we need to do. So let's get on with that. Next up, we need to calculate the equation of the line of steepest fit or shallowest fit. Basically, if I just make this a little bit bigger, we have the dotted trend line, but we could move that trend line upwards and it would still fit within our uncertainties, or we could fit it downwards and it still fits within our uncertainties. Yeah. So we are going to find one of those extremes to then work out our uncertainty in the gradient and the y-intercept. Cool. So to do that, we need to consider the first data point, which is this one right here. Can I select it? Oh. Yeah, the smallest square root length, which corresponds to a period of 0.932 seconds. We left off, I'm reminding myself, right? We have our length and our smallest possible time period, right? Time period, subtract uncertainty, and then our largest possible time period plus uncertainty. And so to plot it on the same graph, what we do is we have our average, right? So if I click the graph, you'll notice we have our x values and our y values. If we insert, so right click H, insert a column just to the right of our average period, and I'll call that error line points. Our first point was 0.902 and our last point was 1.991. So I can actually just delete that. And of course, since that's not the same color, that's probably annoying you. So there we go, error line. Now, we haven't included that in our graph yet. So to include these 2 points, so have a look closely at the graph. When we drag this blue box over one, it has now added, see those 2 orange dots? It has added the 2 data points of 0.447, 0.902, and 1.000, 1.991. And a reminder, we got those from firstly subtracting an uncertainty to get the smallest value, and then adding an uncertainty to the last point to get the largest value. And so if we carefully select, zoom in a little bit, there we go. I selected the 2 orange dots. We can add a trend line. More options, trend line options, linear, display equation on chart. Could do the R² value, but no need. Awesome. And then we have our line of steepest fit. Optionally, you could change the color, but orange looks good to me. Like before, we can increase the font size. Instead of Y and X, we have T and square root of length. And I'm just going to match the color like so. And I'll call this line of steepest fit. And I'll call my other one line of best fit. Like so. Great. So what have we done? We have, for the first point, zoom out, we have found the smallest possible Y value, right, by taking our measurement for one period, subtracting the uncertainty. We have found the largest possible period value at like the longest square root length. We have added an uncertainty. We then, this was all done in a new column. We then selected our graph and ensured, notice how the points just disappeared. Oh, and so did my trend line. That this box selecting the Y values also included the error line points. Once we had that, we zoomed into our graph, selected the orange dots, added a trend line, displayed the equation, and I just changed up the labels a little bit. Cool. And now, that is our linearized graph complete. Draw this line. Yep, that's all done. So we can Control-C, copy, and paste it into our linearized graph with error bars. Like so. Make that nice and big. And you'll notice the line of worst fit goes from the bottom of the first error bar to the top of the last, and it passes through the other 2 error bars, but just not the second one, and that's alright, that's within a reasonable range. But if you find it doesn't pass through your error bars, what you do is you adjust these 2 values. For example, 0.91. Notice how that's made the line a bit shallower. Yeah. Adjust them until they fit just through your uncertainties. Awesome. Onwards. So the home stretch now, we need to state the mathematical equation. Again, like level 2, except this time, including the uncertainties. And then finally, we compare it to the theoretical equation. So from this point, we're actually done with Microsoft Excel. So I'll just save that and go over to my report, my Word document file. So, state the final mathematical equation. Well, I have stated it inside this graph, but that does not include the uncertainties. So I'm just going to type up line of best fit t equals 1.8503 backslash square root L plus 0.1222. So this is currently unrounded, right? We don't have our uncertainty yet. Line of steepest fit 1.9706 square root L plus 0.0207. Now the uncertainty in our line of best fit gradient and y-intercept is the difference between the best fit and the steepest fit. So uncertainty in gradient. So we can write delta m, like uncertainty in the gradient, is equal to the absolute value, so like the difference, the positive difference. So 1.9706, that's the gradient of the steepest fit, take away 1.8503. Let's see what that is on my calculator. 1.9706, take away 1.8503. I got 0.1203. And our uncertainty, right, this is an absolute uncertainty, needs to be rounded to one significant figure. Similarly for the y-intercept, so delta y equals the absolute value, so like the difference, 0.0207, subtract 0.1222. And so you'll notice that calculation gives a negative value, but you just take the absolute, so the positive value. 0.207, take away 0.1222, which gives 0.1015, which again happens to also be one significant figure. Excuse me, it is always one significant figure, but it happens to be the same value of 0.1 after we round it. Cool. So that is our uncertainties. Let's see where we're at. We've found the uncertainty. Yep, excellent. And now we state our final mathematical equation. So in this format right here. So I'll say final mathematical equation. Time period is equal to the, so open square brackets, the gradient, line of best fit, was 1.8503, plus or minus the uncertainty in the gradient, 0.1. But notice our uncertainty is to one decimal place, so we also need to round our gradient to one decimal place. So that's the gradient, square root of length, plus the y-intercept, which was 0.1222. Again, plus or minus the uncertainty of 0.1. That is one decimal place, so we round our y-intercept to one decimal place. And that is our final mathematical equation. With uncertainties, so that is these parts here. There and there. Right, coming from our calculation comparing to the line of steepest fit. And you might recall from level 2, you might have had something like your final equation like that, all as we've done is replace the gradient with square brackets, gradient plus or minus uncertainty, and then instead of the y-intercept, square brackets, y-intercept plus or minus the uncertainty. Alright, and the last step to get our merit is to compare the experimental and theoretical equations. So, with that in mind, we go all the way back up to the start. We remind ourselves what the theoretical equation is. So, now my font's massive. Theoretical equation. Let's make that all. There we go. So we have our experimental, or yeah, I should say experimental equation, and our theoretical equation. Now we need to compare them. So in order to compare, firstly, notice the theoretical looks similar to like our form, where the y-intercept is 0, the gradient is 2 pi divided by square root of g. So we need to work out what that value is before we can compare. So using g equals 9.81. If you decided to use g as a different value, that's fine, as long as you state it and it's reasonable. 2 pi divided by square root of g is equal to 2 pi divided by square root of 9.81, which gives 2.006. So the theoretical equation would become time period equals 2.006 square root L plus 0. So one more time. This is the background equation. All as we've done is put in the constants. So in this case, the only constant was g. For you, another constant might be mass or some other thing that you measured that was a controlled variable. And I found that gradient would be 2.006. So just putting it in a similar format to our final experimental equation, we can then compare. So let's compare. So just looking on the right hand side here, I'm not going to type all this out, but it's the same format. Ooh. So I think the values here are just a little bit different, but let's just step through it. So the theoretical value, which we worked out, of the gradient is 2, rounded to 2.0, rounded to 2 significant figures. The range on R value goes from actually 1.8, because our uncertainty was 0.1, up to 2.0. In other words, our gradient could be somewhere between 1.8 or 2.0. Right, because 1.9 plus or minus 0.1 gives that range. And that shows that our theoretical value is just within the experimental range. Right? When we round the theoretical value, our upper limit is just within the range. Similarly, for the y-intercept, the theoretical value is 0. Right? There is no y-intercept. Our range goes from, what should that be, 0, because our uncertainty was 0.1, up to 0.2, again, plus 0.1 plus or minus 0.1 goes from 0 up to 0.2, which also shows that the y-intercept, the theoretical y-intercept, is just within our experimental range. And lastly, just showing a percentage calculation. So our uncertainty was 0.1 divided by 1.9, which should just be half of that, I believe. And anything like less than 15% is reasonable. You're aiming for less than 10% ideally, to show that the experiment was acceptable. Cool. So, whoopsies. We have stated the theoretical equation, calculated its gradient, and stated its y-intercept, compared the gradients, y-intercepts, and showed a percentage uncertainty calculation. Alright, and that would be almost merit. Right, upon reflection, the things we need to improve a little bit would be our controlled variable description, our accuracy techniques as well, but our analysis was good, graphs were clear, line of steepest fit was good, and final comparison was done well as well. Cool. So that concludes this video series. If I get time, I'll be making the excellence part, but excellence is honestly just about the discussion. And so in the assessment task, let's just have a look. Writing up here, these points right here, so the controlled variables explained in depth and how they would affect your measured variable. Limitations of the theory, so what were the extreme values that you used? For us, or for me, it was 0.2 meters and 1.0 meters. Is this reasonable? What would happen if we took it smaller? Right, how would reaction time play a role? Could we overcome that? What happens if we take it longer? Like air resistance would be more affected. How would that adjust the time period? Would it? Right, think simple harmonic motion. If the amplitude decreases, the time period won't change. So you could talk about things that won't have an impact as well to like demonstrate your level 3 physics knowledge. And any unexpected outcomes, why they might be the case, right, showing your critical thinking. Whew. All right, I think we're done. Go on and finish your practice investigations and see you when I see you.